Okay, so we'll start off by trying to understand this force, van der Waals force. Okay? This occurs between all atoms. So here's a simple atom. Okay. In every atom, by the way, do you guys know how many different kinds of atoms we have? Huh? Here's a list of every one of them. Okay. There are 92 naturally occurring atoms, different atoms. So 92 different elements that are naturally occurring. By the way, 83 onwards, they're all radioactive, meaning they're unstable. And then there's a whole bunch that are man-made. So I believe we made up to, oh, there you go, up to 118. So 92 to 118, that's 26 man-made elements. Okay. And those are very unstable. Okay. But, yep.
Theoretically, there's 126.
Right.
And that 126 is stable again.
Well, it's, okay. How stable is it?
Well, we haven't found it, but theoretically.
Well, there's the island of stability that,
Yeah.
yeah. Yeah, but we haven't found it naturally. Yeah. Okay. In nature. Anyway, okay, so for our purposes, there are 92 different kinds of elements that are naturally occurring. Okay, and here's the deal. Here's the point of this. Okay, so if you take any atom from any of those elements, what you'll find is the center of the positive charge. So an atom, the nucleus has a positive charge, which is surrounded by a cloud of electrons. And the center of the positive charge is exactly on top of the center of the negative charge. Or the center of the negative charge is exactly on top of the center of the positive charge. So no atom has what is called a dipole moment. Okay? So a dipole moment would be if the center of positive charge and the center of negative charges are separated. Okay? All right, so no atom has that. But here's what happens. If you take two atoms and bring them close together, and you gotta bring them roughly about 5 nanometers close. Okay? And what 5 nanometers means is roughly 10 times the size of an atom. Okay? So you take two atoms. If my fists are the size of an atom, if you bring them this close together, here's what happens. Okay? So if you bring them close enough, now they distort each other. What happened here? The nucleus of this guy attracted the electrons of this guy. So the electrons got closer to him, and these electrons repel these electrons. Okay. So actually, the electrons repel them. Okay. So now what happens between these two guys? When these guys were like that, they're not attracting each other because this is neutral, this is neutral. Now, this guy, this positive charge attracts him. Okay? And so there's a weak attraction between these two guys. And this is the van der Waals force of attraction. Okay? You can take any two atoms, bring them close enough, and they'll weakly attract each other. Well, how strong is this attraction? Okay, so this gives you the strength. Okay, do you guys know what a covalent bond is? So the covalent bond between, so here is methane, and the bond between these guys is a covalent bond. This gives one electron, this gives one electron. They share a pair of electrons, and that's a covalent bond. And that's one of the stronger bonds. And you see this, the strength of that bond is about 300 kilojoules per mole. What that number means is to break 1 mole of the bonds. What is 1 mole? Have you guys heard of Avogadro's number? Anybody? Avogadro's number is we'll just say 6 times 10 to the power of 23. Okay. That's Avogadro's number. So it's a trillion. Okay. So 1 mole is a trillion of something. To break 1 mole of these bonds, you need 300 kilojoules of energy. Okay? So these numbers just tell you the strength of a bond. Okay, what we're working towards is, what we want to understand. Have you guys seen a gecko walking on the ceiling? Okay, why doesn't it fall down? Okay, that's what we're going to understand. Okay, that's what we're trying to figure out. Okay, so the gecko uses a van der Waals force. Yep. Okay, so the covalent bond strength is that much. A hydrogen bond strength is about 1/10 of that. And the van der Waals force bond strength is about 100th of that. Okay, or 1/10 of that. So this is a weak force. Okay? But this is important in many situations. Okay, so here's a gecko. Here's the leg. So this is the leg of a gecko. So there, the leg has, millions of setae. Setae are hair-like structures. And these setae, these hair-like structures are further branched. And the spatulae are the tips of these hair-like structures, which are flattened. Okay, so here's a 100 nanometer picture. Here's the flattened tip of those hair. Okay, now what happens is when this flattened tip, so if this flattened tip comes close to a surface, those atoms are close enough. Remember how close do they need to be? 5 nanometers. And those van der Waals forces attract the surface. So it can be any surface. Okay. And then each spatula sticks to the surface, and there's millions of these spatulae. Okay. So the massive cumulative surface area of the spatula allow geckos to cling to the surface using weak van der Waals forces. And all those forces will add up to many times the weight of the gecko. Okay? So a gecko can cling to a smooth vertical wall or even hang upside down from the ceiling. It does with this van der Waals force. Okay? The foot pads are covered with millions of setae. Okay. Each spatula only works if it's aligned very close and flat against the surface. So if this is the surface, and if the spatula was at this angle, then the atoms are not close enough. And the critical angle is about 30 degrees. Okay. So now I've just given you a sort of a clue. Okay. So when a gecko walks, all these spatulae are sticking to the surface. Okay. Now how does it walk to the next step? So here's a very strong attractive force. When you have a strong attractive force, what is the problem? Do you see any problem? What's that? It won't let go. How do you move forward?
Exceed the critical angle.
What's that? So when a gecko walks, so it can't lift its leg up straight like that. If that would require too much force. So how do you solve that problem? You've already indicated that. So you peel your legs. Okay, that's how a gecko walks. Okay. So, so when the spatulae are tilted beyond 30 degrees, they no longer stay close enough for van der Waals force to be effective. So when geckos walk, instead of lifting their whole foot, you couldn't apply a strong enough force to do that. If you tried to do that, you'd leave skin behind. Okay? So they peel their toe like tape. Okay? That's the reason why you don't, you've all taken Band-Aids off. Have you tried taking a Band-Aid off all at once? No. You peel it, and that's what the gecko does. Okay? So the contact breaks gradually, just like peeling off a sticky note, requiring very little force. So this mechanism allows geckos to stick strongly, holding many times its body weight. Okay? And they can detach instantly, almost with no effort. So they can scurry along ceilings. Okay? So what goes in here is the physics of adhesion. but also the geometry of detachment. You have to understand that to understand the walk of the gecko. Okay? And so the critical angle is 30 degrees. When the spatulae are inclined at an angle of 30 degrees to a surface, they're no longer clinging to that surface. Okay? All right. So now we'll talk about drag forces. So when an object moves through a fluid, the fluid exerts a drag force. Okay? So for instance, when you drive your car, half your gas is spent because of this drag force, to overcome this drag forces. Okay? Of course, it's easier to drive a motorcycle in air than in water, for instance. Okay? So the drag forces, the denser the fluid you're traveling in, the greater the drag force will be. Okay? So drag force is a force that opposes the motion of an object as it moves through a fluid, such as air or water. So you experience drag forces due to air whenever you jog, bicycle, or drive your car. So you guys have seen these bicycle riders, road bicycle riders, and when they ride one behind the other, what is that called? Drafting. You guys know why they do that? Okay, so this guy has drag forces, and if you have a second bike riding there, if you ride at the correct place and in the correct alignment, this drag force, the drag force on this guy, can be almost half as much as this guy. Okay, so don't do this, and I've never said this to you, but if you ever tried this driving on a highway, if you drive behind a semi, you can draft. Okay, so you can improve your gas mileage, but it's dangerous. Don't do that. In biology, drag forces are extremely important, and that's what NASCAR car drivers do. They're drafting in. Drag forces are extremely important for microorganisms moving in water. Drag is not a constant force, unlike friction forces, which are between two solid surfaces, because the drag force, this force, depends on the speed of the guy. Okay? So do you guys know when your car is most efficient? What speed do you need to drive to get the best gas mileage? I'm sorry, about 55 miles an hour. Okay, and as you drive faster and faster, this force increases, and you're spending more and more gas on driving. Okay? Drag is a complex force, and there are two rather different physical causes for drag. Okay? For large objects, such as flying birds, most of the drag occurs because the bird must push the air in front of it. Okay, so when a plane is flying, it's got to do the same thing. It's got to push the air out of the way. Okay, this drag is caused by inertial forces that arise because of a fluid mass. Okay, so it's got to push all the air out, and that's called inertial drag. There's a second cause. Okay. The drag on smaller unicellular organisms swimming through a liquid is mostly due to viscous forces. Okay, so drag can occur either via inertial forces or viscous forces. What is this? From the fluid molecules sticking to one another. Okay, so here's a small animal, and it's trying to swim through water. These molecules are sticking to each other, and they stick to the surface, and so they're pulling the guy back. Okay, so if this unicellular organism is trying to move that way in a liquid, the liquid molecules attract each other and they stick to the skin and pull them back. Okay, so that's viscous forces. So I'll give you an example. If you can swim in water, and you can swim underwater too, but if you try doing that in honey, it would be impossible. That's because honey molecules attract each other, and I'll show you numbers in a little bit, and they'd stick to your body, and the drag forces would be too large. So there are two causes for drag forces. Okay, What is a drag force again? A drag force is a friction force when you try to move in a fluid. And what is a fluid? A fluid is air and liquid, okay? In many situations, only one of the drag forces is significant. Either this matters in your life or this matters in your life, okay? In our life, for us, it's this matters. This is what matters, okay? So when you run and jog, what you're doing is you're moving the air out, and you're having to move the mass and the drag forces because of inertial forces. There's this number called the Reynolds number that tells you what plays the major role in your life. Okay? And here's how the Reynolds number is defined. Reynolds number is inertial forces divided by the viscous forces. Okay, if in your life inertial forces are more significant and viscous forces are small, if this is big and this is small, that means Reynolds number is big. Okay, so a bigger Reynolds number means inertial forces are significant in your life. If Reynolds number is small, then it's viscous forces that are more significant in your life. All right, so we will talk of two regimes. We'll talk of Reynolds number, which are bigger than 1,000, so only inertial forces are significant. And we'll talk about Reynolds number that are less than 1, okay? And so viscous forces are significant here. Okay. So we'll talk about amoebas swimming in water. So for them, Reynolds number is less than 1, and viscous forces are significant. For you going for a jog, and for a big fish swimming in water, Reynolds number are large, and so inertial forces are significant. Okay? It's a dimensionless number. That's force divided by force. It's just a number, and it has no units. And by the way, in this formula, rho is the density of fluid you're going in, you're moving in. V is your speed. L is roughly your dimension. And again, you don't have to remember these formulas. Eta is the viscosity of the fluid. Okay? So it depends on the density, size of the object, its speed, and viscosity of the fluid. So here's viscosity of the fluid. It tells you how much friction there is. Okay, the friction it's related to the friction in the fluid. Okay, you can see that for water, the viscosity is so in SI units, it's about 1,000th, and for olive oil, that's almost 10 times. That's a 10 to the minus 1. So olive oil is 100 times more viscous than water. Okay. And we'll have something to say about that in a little bit. Honey, look at this. Honey is 10,000 times more viscous than water. So what that means is if you try to swim in honey, it's 10,000 times harder than swimming in water. Okay. All right, so here's the salmon swimming. Here's the Reynolds number for salmon swimming. So this would be the density of water. There's the density of water. There's the speed at which it's swimming. It's 0.5 meter a second. That's about 2 foot a second. And that's roughly the size of so here's a salmon, and that's roughly 15 centimeters, 1/2 foot. Okay. So, and there's the Reynolds number. So the Reynolds number is greater than, this is the large Reynolds number. And so what inertial forces are the dominant forces. Okay. So when a salmon is swimming, what is it trying to do? It's moving the water out of the way. Okay. So inertial drag forces dominate. Okay. So high Reynolds number, okay, if a Reynolds number is greater than 1,000, it's considered high. Okay. And then the drag forces are proportional to the speed square. Okay, so here are the drag forces, and it's proportional to the speed square. So what does this mean? If you double your speed, the drag forces quadruples. Okay? If you double your speed, so it gets harder and harder to move faster and faster. Okay? This is the drag coefficient. Okay? So the drag coefficient for your car, for instance, is much smaller than for a UPS truck. Okay? So when they say they're trying to make a vehicle aerodynamic, what they're trying to do is they're making this number smaller. Okay? Rho is the density of air, and A is the area of cross section. So let's say this is the car coming at you. This would be the area. Okay, area of cross section. Area in a direction perpendicular to the direction of motion. Okay, so that's the drag force. Anyway, the important thing is the drag force is proportional to the square of the speed. You double the speed and the drag force quadruples. Okay. Reynolds number is high for most ordinary objects, balls, when you throw a baseball through air, birds, cars moving through air, and so on. And for fish moving through water. Okay. For high Reynolds number, the drag force is proportional to the square of the speed. So here are some of the drag coefficient. There are those numbers, like I said. Okay. So for the Prius, it's 0.24. For swimming fish, it's 0.15. Look at this, commercial airlines. For an airline, the drag coefficient is 10 times smaller than for your Prius. Okay. For a bird in a dive, it's that. Okay. It's the same as a pitch, as a baseball. Okay. For a running person, it's about 5 times greater than a Prius. Okay. It's 5 times harder to run than drive a Prius. Yep.
Drag coefficient would, is it linear? So the drag coefficient of an airliner, is that at altitude or at like?
Yes, well, yeah, I would imagine so. It's because the air is less dense and stuff. But well, I guess it's just that much more aerodynamic. Well, an airliner, when it's flying, it doesn't have wheels sticking out like a car does. That probably gives you the...
Yeah. So, you know, for the flight levels where the air is thinner, you can.
So the drag coefficient, that is independent of the density of air up there.
Oh,
Yeah. Yep. Did you have a comment back then? All right. All right, so now we'll talk about terminal speed. So this drag coefficient was the drag forces we wanted to set you up for a terminal speed, and we'll talk about, you guys have seen, you might have seen a squirrel jump off a tree and live, and it can do that all the time. I couldn't do that. So what's the difference? Okay, so we'll figure this out. All right, so let's say I jump off a plane. What will happen? The force of gravity will act on me, and I'll start moving faster and faster. Okay, and as I move faster and faster, what happens is this drag force increases. Because remember, the drag force depended on my speed. It was proportional to my speed square. So as I'm going faster, this drag force is increasing. Eventually what will happen, this will equal my weight, and now the net force on me is 0, and now I can't speed up anymore. Did you guys understand that? So this drag force can increase with your speed, This force is constant, so this force is speeding you up, except that this force is increasing. And so eventually you reach a speed when this force is equal to that, and you won't speed up anymore, and you have reached terminal velocity. Okay. So you can drop any object in from air, and everything will reach terminal velocity. All right, so this can happen if you throw an object horizontally. If a fish is swimming in water, this is the applied force, there's the drag force, and when the drag force equals the applied force, then the fish has reached terminal velocity. When a fish is swimming at constant speed, that's what's happening. Okay, the force it's applying by wagging its tail is equal to the drag force. So the steady, unchanging speed at which drag exactly counterbalances an applied force is called the object's terminal speed. Yeah. So here's a skydiver, and here's a mouse falling in air. Okay. So skydivers reach terminal speed while falling. Drag balances gravity when this happens. By the way, did you guys know that what is the skydiving capital of the world? Anybody know that? DeLand. Yep. Yep. So you're living right next to the skydiving capital of the world. Yep. All right. So your terminal velocity when you fall like this is about 120 miles an hour, and if you nosedive, it's about 180 miles per hour. Yep. And we'll see why. That's because this area of cross-section is higher than this area of cross-section. Yeah. A fish reaches its maximum speed, also a terminal speed, when the drag of the water equals the opposite to the propulsion force the fish generates by lateral motion of its tail. Okay, so when the drag force is equal to the weight, you have reached terminal velocity, and there's the terminal velocity. So the terminal velocity is twice your weight divided by the drag coefficient divided by the density of air in which the density of the fluid you're falling in. Okay, so if you're skydiving, that's the density of air, and that's the area of cross-section. Okay, so when you fall like this, that would be your area of cross-section, and when you fall like this would be your area of cross-section. Okay, so since this area is much larger than this area, your terminal velocity when you're falling in this configuration is 120 miles an hour. When you're falling like this, that area is smaller, you're falling at 180 miles an hour. Okay, so for a skydiver falling in this configuration, the terminal velocity calculation is shown here. It's about 40 meters per second, which is roughly about 100 to 120 miles an hour. It's about 90 miles an hour, but the actual value is that. Here's the terminal velocity for a mouse. This is why we did this. It's about 10 meters per second. That's about 20 miles an hour. Okay, so it doesn't matter if a mouse falls from an oak tree or it falls from, if it jumps off a sequoia tree or a redwood tree. It would be hitting the ground at 25 miles an hour, and it's able to survive that. It's even less, okay? Small animals can usually survive falls from any height because of their terminal speed is not fast. Many tree-dwelling animals, such as flying squirrels, can extend flaps of skin to increase their area and fall even slower. So what are they doing? See, they're increasing this guy. If you increase the area, that's what the flaps are about. Your terminal speed is smaller. Okay, and you can survive the fall. Did you guys understand that? All right. So here is a mushroom, and there are the spores and stuff like that. Okay. A spore released from a fungus settles to the ground at about 20 millimeters per second. So this spore reaches terminal velocity. It's falling 2 centimeters a second, which is about an inch a second. I guess so it's falling that fast. Yep. The Reynolds number here is less than 1. So when the Reynolds number is less than 1, what is the dominant force? Viscous forces are the dominant forces. Okay? It's the stickiness of the air that matters. It doesn't have to worry about pushing the air out of the way. Okay? So for low Reynolds number, the drag force is now proportional to the speed. See, for low Reynolds numbers, the drag force is proportional to the speed, and it's also proportional to the viscosity. Remember, the viscosity of honey was what, 1,000 times greater than the viscosity of, 10,000 times greater than the viscosity of water. Okay? So for small objects to move through honey would be much harder, 10,000 times harder than moving in water. Okay? So this force is called the Stokes law. Now the Stokes law applies to round spherical objects and stuff like that, but we'll apply it to use it for all small objects. The expression for viscous drag on a sphere is called Stokes law. So this is called Stokes law. And the drag forces, like friction forces, are always in the opposite direction. Okay? Okay. So an object reaches its terminal speed when the drag force exactly balances the applied force. Okay, so when an organism wants to move forward, there's the applied force, and when the drag force equals the applied force, it'll reach terminal velocity. So motion at low Reynolds number is almost entirely constant speed at the terminal speed. So small microorganisms moving in water, they're always moving at terminal speed. And soon as they start applying effort, they reach terminal speed. Okay? And soon as they stop applying effort, they stop. Okay? So here's the model of a flagella, which a microorganism uses. It's a hair-like structure, and when it wants to move forward, what it does is it spins the flagella. You guys have seen those Chinese dancers do the ribbon dance? Okay. So it's like a ribbon, and this motion is what's employed. And what this does is it pushes the fluid backwards. And then what does the fluid do? As per Newton's third law, this flagella motion pushes the fluid back, and the fluid pushes you forward. So if this was a microorganism, it starts rotating its flagella, and it starts moving. Okay, and it reaches terminal velocity almost instantly. The instant it stops moving the flagella, it'll stop. Okay. All right, so from protozoa swimming in pond water to bacteria moving in intercellular fluid. So in your intercellular fluid, the bacteria essentially move this way. Okay. Biology is filled with examples of motion at extremely low Reynolds numbers. A 1 micrometer bacteria moves at a typical speed of 30 micrometer per second. Okay, look at this. This is interesting. A 1 micrometer bacteria moves at 30 micrometers per second. So it'll move 30 times its body size in 1 second. Okay. So for runners, what is this maximum speed at which a runner moves? I'm sorry? 10 meters per second. So a 2-meter guy moves at 10 meters per second. So the fastest you're moving, Usain Bolt, is about 5 times your body size. and we are moving through air. Look at this guy. This is a microorganism moving at 30 times its body size and moving in fluids. Pretty good. Okay. Anyway, the Reynolds number is 100,000. Okay. Life at low Reynolds numbers is very much at odds with our everyday experience. It's very counterintuitive. Okay. When a force is applied, the object reaches its terminal speed almost instantaneously and then moves at constant speed. When the force is removed, the object comes to a dead halt almost instantly. Yeah. So, okay, there's no coasting at the microorganism level. Yeah. So, you can swim through water because your hands are able to push the water away from you. If you try to swim through an extremely viscous fluid like honey, your back and forth stroke would cause you to rock back and forth and you would not go forward. Okay, so that motion was not good. So microorganisms had to develop a new technique to move in viscous fluids, and this is what they came up with. So the flagella, and they use cilia to micro hairs, but the effect is the same. Okay, so again, you can see that this flagella is rotated. It pushes water, and that is what propels. And the flagella push the water back, and according to Newton's third law, the reaction force pushes the organism forward. So this is a simple model of a flagellum like the one bacterium use, is basically a rotating corkscrew. The rotary motion enables the flagellum to apply a continuous push to the fluid. The fluid applies by Newton's third law, applies a reaction force to the organism in the opposite direction. Okay. So here the protozoa are propelled by cilia. The beating motion of cilia is more complex than the motion of the rotating flagellum. It's more complex than that, but the net effect is the same, a constant push in the. Okay. So here's a Chlamydomonas. It's a unicellular green algae. It moves at 200 micrometers per second. Yeah. It uses a pair of flagella. And you see, soon as it stops rotating its flagella, it will come to stop in 15 microseconds. Yeah. So it comes to stop almost instantly. Yeah. The graph shows the speed of one algae after it ceases swimming and comes to a stop very fast. All right, now we'll talk about springs, because most biomaterials exhibit elastic behavior. Okay. Your tendons, when they stretch, they store energy. And you guys remember what animal uses that fact? Kangaroos. Okay. How much of the energy can you get back stored in the tendons? 90%. Okay. And that's why they're so efficient at high speeds. Okay. So springs and elastic forces. So here is the unstretched position of the spring. If you stretch the spring, what does the spring do? Anything attached to the spring, it pulls back. If you compress the spring, anything attached to the spring is pushed that way. So what the spring is trying to do is, if you have a stuff attached to the object, if you this is called the equilibrium position. If you disturb it from the equilibrium position, the spring is trying to bring it back to the equilibrium position. So the force is called a restoring force, because it's trying to restore the system to the original configuration. So this force is a restoring force. Okay? By the way, so this force is given by Hooke's law. Okay? And what this tells you is the following. X is how much you have disturbed it from the equilibrium position. This is called the spring constant. K is the spring constant. And this tells you how stiff the spring is. Okay. So stiffer the spring, greater the force you need to stretch it. And also, okay, if you stretch a spring by X, this is how much energy you store in it. So this is the potential energy. That's how much energy you store in it. Okay. So your tendons act like a spring. They have a spring constant. If you stretch the tendon by that amount, that's how much energy you store in the tendons. Okay. If you stretch a rubber band or a spring, and by the way, so here's another thing you might have experienced. Okay. So you guys have all taken a rubber band and you stretch it. After you've stretched a while, does it get easier or harder to stretch it more? It gets harder. Try it at home. Okay? So what is happening is, for low stretching, the spring constant of the rubber band is smaller, so it's easier to stretch it. And when you stretch it more and more, the spring constant becomes harder and harder. And that happens for the spider web as well. Okay. So the spider silk and all that. So they have low spring constants when you're initially stretching them, and then as you stretch them more and more, it gets harder. It happens to the DNA molecule as well. For the DNA molecule, you can stretch it easier initially, and then it gets harder. Okay. So if I stretch this and let go of the object, what happens? The spring will bring it back. Okay, so you stretch a rubber band and let go of the rubber band. What happens to the rubber band? It comes back to its original shape. Okay, that's elastic behavior. How many times can I do that? As many times as you want. Okay? So the elastic behavior is, if you don't break it and if you do not permanently deform it, the elastic behavior is exhibited as many times as you want. Okay? So biological elasticity occurs at the molecular level. Nucleic acid and proteins can be stretched. And at the organismal level, tendons exhibit elastic behavior. Your blood vessels exhibit elastic behavior. Every time your heart beats, the blood vessels stretch to accommodate the increased blood flow, and then they collapse back. Okay? How long does that happen? All your life. Okay? So they have to exhibit elastic behavior forever. Okay? Well, even bones exhibit elastic behavior. Okay, so let's say when I jump and land, what happened? My bone compressed a little, okay, and then it'll stretch back. Nearly everything stretches, compresses, flexes, bends, or twists, exhibits a restoring force and can be called elastics. Okay, so here's Hooke's law. There's here's the spring, here's the unstretched position, and if I stretch it there, the force that the spring applies is K minus Kx. Okay. This is X. The minus sign just telling you when X is positive, the force is in the negative direction, and when X is negative, the force will be in the positive direction. The spring constant is a property that characterizes the spring. If K is large, it takes a large pull. If K is large, it takes a large force to cause a significant stretch. Okay? And we say the spring is stiff. Many biological materials such as tendons and bones behave much like springs when they are only slightly stretched or compressed. Okay, so here's the spring constant of a DNA molecule. So here's a DNA molecule. Okay, this is what is called a optical tweezer. Okay, so here you can anchor a DNA molecule, and you can hold this other end with two laser beams that are focused. Okay, that's called an optical tweezer, and most UF has these things and all of that. And you can apply a force and stretch the DNA molecule. Okay. And you see this is the linear behavior. As long as you're stretching it to about 250 nanometers, 250 nanometers is about 3,000 atoms width. Okay. The stretching force is linear. Okay, so this is the linear region. And if you try and stretch more and more, as the slope increases, the DNA molecule is getting stiffer. What that means is, so the slope of that line, the slope of the line is K, the spring constant. And as the slope increases, the spring constant is getting higher, just like that rubber band. As you stretch it more, it gets harder to stretch the longer you've stretched it. Okay? All right, so the elastic behavior is shown by many of the biological systems. Okay? So how did this octopus move? How does it move? I'm sorry?
Propulsion.
Yeah, propulsion. So what does it do?
It
So
exerts a force behind it, which then moves it forward.
I'm sorry?
It pushes backwards with its arms, which cause it to move forward.
Actually, what happens is it squirts water out. It's like a rocket. Okay?
Okay, that's what I meant.
Okay, well, so it squirts out water, and the reaction force is the propulsion. Okay, a system with internal source of energy, such as ATP or gasoline, can use this energy to drive itself forward. So you do need a source of energy. Okay, we call this propulsion. It's an important aspect of walking, running, and swimming, etc. So it depends on interacting forces. An octopus propels itself by expelling a jet of water. Okay, it's like if you shoot a gun, you recoil. Okay. So before it moves, something called its momentum is zero, and when it propels water, the reaction force, when it squirts water out, the reaction force propels it forward. The animal pushes on water, and by Newton's third law, the water pushes on the animal in the opposite direction. Okay. All right, so, and again, you need energy to do that. All right, so that finishes this chapter.